Okay, sorry for the interruption. Let's again recap what are the contents which is there in this particular lecture. So we'll be talking about the application of magnetic materials, then giant magnetoresistance materials and their applications. After this, we'll talk a little bit about ferroelectrics and then the application of ferroelectric ramps. Then we will cover magnetoelectric effect, then multiferroic materials and their applications. And with this, we will come to an end with the magnetic material part. So hard magnetic materials, just recapping what we had discussed in the last lecture. So in the hard magnetic materials, what you have is a very large coercive force. As you can see over here, these are hard magnetic materials. The coercive force is very high. You have a perfect hysteresis loop as shown over here. The hysteresis loop of hard magnetic materials, a very characteristic hysteresis loop you get in case of hard magnetic materials. So what are the different kinds of hard magnetic materials which we have seen over the years? So you have steel, you have ferrite, you have alnico, you have samarium and cobalt alloys, and then you have NdFeB. These are all different kinds of alloys. So you see what is happening in this case with the different dimensions which are given. So relative magnetic volume for the same magnet energy. So for a steel, if you require this much amount of volume, in case of NdFeB, the same kind of magnet energy you will get with this little volume. So the need for enlarged energy densities at different operating temperatures is the main motive for the development of these rare earth permanent magnets. Most importantly, this comprises the less dysprosium containing Nd2Fe14B type magnets with much improved temperature stability for electromotor applications at around 450 Kelvin. So these have all these different applications. So at different temperatures, you have these different magnetic materials giving you different kinds of magnet energy. So the main point is to get as much amount of magnet energy as possible with a broader temperature of operation. Then what are the different application of magnetic materials? So hard magnetic materials, we have a wide range of applications. As you can see, in the automotive industry, you find magnets being applied in motor drives for fans, for wipers, for the injection pumps, then control for seats, windows. All this is nothing. They are all having some kind of hard magnets being utilized in this kind of applications. Then in telecommunication industry, for the microphones, loudspeakers, telephone ringers, so you have all these different kinds of hard magnets being used. Then in data processing, in the printers, stepping motors, disk drives, actuators. In case of consumer electronics industry, the home computers, your clocks, DC motors for showers, etc., they all are having hard magnets. Then electronics and instrumentation, you have the energy meter disk, sensors, dampers. For industrial applications, you have the lifting apparatus, which are having hard magnets, robotics in your different meters. Then in aerospace industry, you have auto compass, the couplings, instrumentations. In biosurgical, you have NMR, you have MRI body scanner. So for all these different applications, what you need is a magnetic material. For soft magnetic material, what is the difference between hard and soft? In case of soft magnetic material, you will have the HC or the coercive field, which is very, very less. So they are very much useful for power electrical applications such as in generators, in distribution transformers, and also a broad assortment of motors as well as in electronics where a mass of inductive components is required. So you can see these different kinds of examples which are given in this particular plot. You will see the different kinds of soft magnetic materials. And on the x-axis, you will find the saturated magnetic flux density, whereas on the y-axis, what you have is the permeability of these different soft magnetic materials. So let's see now what are the different direct current applications for the soft magnetic materials. So in this case, how you work is the material is first magnetized to carry out an operation, and then it is demagnetized at the last part of the operation. So for material selection, the main consideration, obviously, as I showed in the last slide, it is permeability. High permeability is required for good material. And this is generally used in the field of magnetic shielding, electromagnetic pole pieces, and to activate solenoid switch. Permanent magnet uses this kind of material to make a path for the different flux lines. So these are the different DC application of soft magnetic materials. When you look into the AC applications, these are generally used in power supply, transformer, DC-DC converter, and electric motors. So in this case, how it works, the material will always be in a magnetized state throughout the time of operation. And this is being done by it being magnetized in one direction to other as a continuous cycle. For material selection, the main consideration in this case is the energy loss in the system. The energy loss occurs because the material is cycled around a hysteresis loop. A good material should have the smallest possible energy loss. So that is why your hysteresis loop should be as thin as possible. So you should have for these kind of application, you need soft magnetic materials which has the smallest amount of energy loss per cycle. So now we have functional magnetic nanoparticles. When we are talking about nanoparticles, so these are the magnetic nanoparticles which are having their spin oriented in one particular direction, as I talked about the single domain particles in the last lecture. So here you have quantum dots. You can have quantum dots, which are basically the applications can be in multimodal imaging, nano drugs, which are used for drug delivery as well as for magnetic resonance imaging. Or you can have different kinds of metallic magnetic nanoparticles, which are again used for multimodal imaging as well as multivalency kind of thing are also used. Then you can code these materials using antibodies or DNAs or ligands or receptors or dyes. When you're coating it with antibodies or DNAs, the potential applications are specific binding and drug delivery. Whereas when you are having ligands or receptors attached to it, the applications can be in bacteria detection, in protein separation. Whereas when you are having dye molecules, you can again use it for multimodal imaging. So these are the different applications of functional magnetic nanoparticles. So now coming to the next topic, which is magnetoresistance. What do we mean by magnetoresistance? So it is the dependence of the electrical resistance of a sample on the strength of an external magnetic field. So mathematically, how we will give this, how we will express this value, this delta H is nothing, but it is the difference between your resistance when you are applying a particular field H and the resistance when there is no field being applied, and you are dividing this difference with your resistance when there is when the H is 0, that is when no external field is applied. So now why this term, why we are talking about magnetoresistance? Because nowadays you hear a lot about giant magnetoresistance. A lot of materials show giant magnetoresistance. What do you mean by that? This indicates that the value for this delta H for multi-layer structures significantly exceeds the anisotropic magnetoresistance. This is very important. Significantly it exceeds the anisotropic magnetoresistance, which has a typical value between few percent. In case of giant magnetoresistance, this value can be many times more. So this effect, it was discovered by Grunberg and Fert in 1988. And this is a large change in the electrical resistance, which is induced by application of a magnetic field to thin films composed of alternating ferromagnetic and non-magnetic layers. So this change in resistance in general, which is a reduction in the resistance, is related to the field-induced alignment of the magnetization of these magnetic layers. So in the first experiments, the fields were composed of layers of iron, which is ferromagnetic, and chromium, which is non-magnetic, with a typical thickness of a few nanometer, and the current was applied in the plane of the film. But you should remember that GMR effects, it can also be obtained when the current is applied perpendicular to the layers. So the origin of this giant magnetoresistance is a dependence of the electrical conduction in ferromagnetic materials on the spin state of the carriers. So basically how the spins are getting changed, or the electrons are changing, that is giving you the origin of the giant magnetoresistance depends on the spin state of these particular carriers or the electrons. So let's explain this a little bit. What happens is, in the giant GMR, what happens is there is a change in the electric conductivity in a system of metallic layers when an external magnetic field changes the magnetization of the ferromagnetic layers relative to each other. So pictorially, if I represent it, what you see is over here, you are having one ferromagnetic layer here, another ferromagnetic layer here, which is sandwiched, and the non-magnetic layer is sandwiched between these two layers. So what happens? The effect size is defined as delta R by R. So what is it? It is R when this particular magnetization in this ferromagnetic layers, in this alternate ferromagnetic layers, they are anti-parallel to each other, which is subtracted from the resistance when they are parallel to each other, and this entire thing is divided by your resistance when these two layers are having magnetization which are parallel to each other. So alternatively, the ratio is sometimes defined also with R antiparallel as the denominator. And this effect, it originates from the spin-dependent transport of electrons in the magnetic metals. So what is so intriguing about this GMR is that it enables a sensing of external magnetic field strength in electrical units in between two electric states of resistance. So the spectrum of successful applications of GMR technology is impressively broad. It ranges from application in the air and the space or automotive industry. Then you find a lot of application in NDS, which is non-destructive material testing, and compass functionality in the mobile phones. Your mobile phones, you see, it points towards the north. So how do you do that? For that, basically what you use is a GMR kind of material. Then you have different biomedical techniques like biometric measurements of eyes and biosensors, detection of all these viruses. For all these different applications, what you need is a GMR material. So let's look into it pictorially, how we can pictorially represent this particular change in resistance. So as you can see over here, the resistance is the y-axis and your x-axis is the field which you have applied. So change in the resistance of the magnetic multilayer as a function of the applied magnetic field. This is nothing but GMR. So the magnetization configurations, these are indicated by arrows over here. As you can see, these are parallel to each other. In both the cases, they are parallel to each other. The magnetizations, they are aligned anti-parallel. As you can see, when the field is 0, that is at this point, these are aligned anti-parallel to each other. And when the external magnetic field H is larger than the saturation magnetic field, then the magnetizations, it becomes aligned. So when this H value is higher than your Hs value, or which is a saturation field, then basically the magnetization, it gets aligned to each other. And the graph which you will plot, this M versus H plot, is going to look somewhat like this. So this is the magnetization curve for the multilayer. So now let's find out what is the origin or the microscopic origin of this GMR effect. So first, the electrical conductivity in metals, it can be described in terms of two largely independent conducting channels corresponding to the upspin and the downspin electrons, which are distinguished according to their projection of the spins along the quantization axis. So the upspin and the downspin electrons, they do not mix over long distances, and therefore this electrical conduction, it occurs in parallel for the two spin channels. So the band structure, if you remember the band structure that's shown in a ferromagnet, is exchange split. So the density of states is not the same for the upspin and the downspin electrons at the Fermi energy. Now the scattering rates they are proportional to the density of states. So the scattering rates and therefore resistivities, they are going to be different for electrons of different speeds. So basically this rho up is not equal to your rho down. So then it is assumed that the scattering is strong for electrons with spins which are anti-parallel to the magnetization direction, and it is weak for electrons which are having spin parallel to the magnetization direction. So this is supposed to reflect the asymmetry in the density of states at the Fermi level, and this is in accordance with Mott's second argument. So for the parallel aligned magnetic layers, the upspin electrons, it will pass through the structure, as you can see over here, almost without scattering, because their spin is parallel to the magnetization of the layers. On the contrary, when you're having this downspin electrons, these are scattered very strongly within both the magnetic layers because their spin is anti-parallel to the magnetization of the layers. So what you are seeing over here is, in one case you are having a lot of scattering, in the other case you are having much less scattering. So since conduction occurs in parallel for the two spin channels, the total resistivity of the multilayer is determined mainly by highly conductive upspin electrons, and it appears to be low. Now for the anti-parallel aligned multilayer, both the upspin and the downspin, as you can see over here, both the upspin and the downspin electrons, they are scattered strongly within one of the ferromagnetic layers. Because within one of the layers, the spin is anti-parallel to the magnetization direction. Therefore, in this case, the total resistivity of this multilayer is going to be high. So what are the different types of GMR? So that was the origin, the microscopic origin of the giant magnetoresistance effect. Now we have to see what are the different types of GMR materials which we have. So now, as I've shown over here, you can see these 4 different kinds, A, B, C, and D. And now I will describe to you what exactly each of this type of GMR are. So one is this magnetic multilayer, which is A. D is the pseudo spin valve. C is the spin valve. And D is the granular thin film. So now we will discuss what exactly are these different types of giant magnetoresistance materials. So in the magnetic multilayer A, the ferromagnetic layer, this is separated by non-ferromagnetic spacer layers. As you can see over here, this dark one is ferromagnetic and the lighter one is the non-magnetic layer. Now, due to the antiferromagnetic interlayer exchange coupling, they are aligned antiparallel at zero magnetic field, as is indicated by the dashed and the solid arrows, as you can see over here in the ferromagnetic material. As you can see, because of that antiferromagnetic interlayer, what you have is they are aligned anti-parallel at the zero magnetic field. Now, at the saturation field, the magnetic moments are aligned parallel. So when they are saturated, then they will be aligned parallel to each other, which are nothing but the solid arrows. Now, in case of the pseudo-spin bulb, what happens is the GMR structure, it combines both hard and soft magnetic layers. So one, in case you have this ferromagnetic layer is hard, this is sandwiched by a non-magnetic layer, and then you have a ferromagnetic layer which is soft. So due to what is the difference, inherent difference between hard and soft ferromagnets? It's the coercivity. So they have different coercivity. So when the switching of this ferromagnetic layer, they are occurring at different magnetic fields, they provide a change in the relative orientation of the magnetization. And this basically gives rise to that GMR effect. In case of spin bulb, what you are having? The top ferromagnetic layer is pinned by the attached antiferromagnetic layer. Okay, so you have an antiferromagnetic layer on top, and then to it you have a ferromagnetic layer. So this ferromagnetic layer is pinned to this antiferromagnetic layer. So the bottom ferromagnetic layer, as you can see over here, this is free, and this rotates by the applied magnetic field. So this is how the GMR effect is taking place in case of a spin bulb. Whereas when you move into the granular thin film, what is happening? You are having magnetic precipitates which are embedded in the non-magnetic metallic material. As you can see, these are the granular precipitates. They are embedded in the non-magnetic material, which is given in this light color. So in the absence of the field, the magnetic moments of the granules, they are randomly oriented, and the magnetic field aligns the moments in a certain direction. So again, this again gives rise to a GMR effect. So what are the different applications of this giant magnetoresistance? So the largest technological application of GMR is in the data storage industry. So the GMR read head sensor is a hard disk which is built using a spin valve. So the spin valve resistance demonstrates a steep change in the small field ranges which is close to zero. Now, as the magnetic bits on the hard drive pass under the read head, then what happens? The magnetic alignment of the sensing layer in the spin valve, which changes, resulting in this resistance change. So you have a change of resistance as soon as this, when you are having this magnetic bits on the hard drive, they are passing under this read head. The magnetic alignment of the sensing layer will change in the spin valve, and this results in a resistance change. So now as the read head is passing over the disk, what is happening? The free layer, it shifts its magnetic orientation and it matches with that of the bit. So sometimes the direction of this free layer magnetic field is aligned with the field of the pinned layer, which never changes, and sometimes it is opposite. So when they are aligned, what will happen is most of their electrons will share the same up or the down spin. Now as some of these electrons are passing through the layers in the form of the current, then there is going to be a minimal scattering, and this low resistance means that a current is going to be detected and the computer will compute it as 1 bit. Now when the free layer's magnetic orientation, it switches to the opposite than that of the pinned layer, then there is going to be a very different result. The electrons in the two layers will now have opposing spins. So as the current passes through the magnetized layers, those electrons will scatter in one or other, in one or the other of them. So this will result in a much weaker current and a 0 bit. So you have a 1 bit and a 0 bit, and this is how basically the reading is happening. So this is basically the giant resistance materials. Now coming to the next topic, which is ferroelectricity. What is ferroelectricity? We talked about ferromagnetism in the last class. So similarly, we have something which is known as ferroelectricity also. So what is ferroelectricity? It is the characteristic of certain materials that have a spontaneous electric polarization that can be reversed by the application of an external electric field. So getting into the details, what is this? So you apply a very small electric field. It is so small that you are not able to switch the domain alignments. So then in that case, the material will behave as a normal dielectric. So you have the polarization is directly proportional to the applied electric field. Now you keep increasing this E. So what happens? Your domain starts flipping and your polarization value is going to increase rapidly. Now, when all the domains are switched, what is going to happen? We will reach a saturation. We will achieve a saturation. So, if you now remove that electric field, what is going to happen? Do you think it is going to come back to zero? No. What you will see is basically a hysteresis, as you have seen in case of magnetization. So, I have applied a field, it went up over here. Now, when I bring down the field, it is not that it is going to follow the same path. What is going to happen? It will come back to a certain point where you will still have some polarization even when the electric field is zero. And then when you apply a negative bias, in that case, it will take the negative bias, and after a certain point only, it is going to lose the entire polarization. So what you have is a polarization hysteresis. So the essential feature in this case of a ferroelectric is not that there is a spontaneous polarization, but this spontaneous polarization can be reversed by the application of an electric field. So this is basically the essential feature of a polarization hysteresis. So now there is a very close connection of your crystal system with the ferroelectric. Whether a material is going to be ferroelectric or not can be very easily stated by looking into the crystallographic and the crystal classification of that particular material. So now in the first 2-3 classes of this advanced materials chemistry course, you have done crystallography a little bit in detail. So you know that there are 32 different crystal classes. So all these 32 classes are shown over here. So now this crystal classification of a material, they will have immediate implications for ferroelectric effect. Out of these 32 crystal classes, 11 of them, they are having a center of symmetry. That is, they are centrosymmetric, and hence they will not support ferroelectricity. So the ones which are centrosymmetric has been highlighted in black over here. The orange ones are the ones which are non-centrosymmetric. So out of 32, 11 are already cancelled. They are not ferroelectric. Now then again, of the remaining 21 which you had, there is one group, this is this O group over here, 432 it is known, this also excludes ferroelectricity. Now the remaining 20 which are marked as in orange, these are the ones which all exhibit the piezoelectric effect, okay. So what is the relation between a piezo, pyro and a ferroelectric point groups? So let's see, so in total you have 32 point groups as you can see over here, out of which this 11 are centrosymmetric. So these are not going to show you any kind of ferroelectric or piezoelectric properties. Out of this 21 remaining non-centrosymmetric, you have one exception, which is that O group, which I had shown in the last slide. Now you have 20 of them left, which are basically nothing but piezoelectric. Now out of this 20 piezoelectric, you have 10 non-polar ones, which you shouldn't bother about, but you have 10 which are polar, and these are all known as pyroelectric. So out of these pyroelectric materials, the ones which show reversible polarization, these are known as ferroelectric materials, whereas the others which are non-reversible polarization, they are not called ferroelectric. So if we look into this kind of a diagram, you have piezoelectric materials in which there is a subset which is pyroelectric, and inside that pyroelectric, the ones which are showing reversible polarization, they are the ferroelectric materials. So you can see all ferroelectric materials are definitely you can say all piezoelectric materials will not be ferroelectric, but all ferroelectric materials definitely fall into the major class of piezoelectric. So one of the topmost examples of a ferroelectric material are the perovskites. So perovskites, you all know, these are natural. This is a naturally occurring mineral, and the chemical formula is that of a calcium titanate. So this is a prototype of many AbO3 materials, which are very important in case of ferroelectrics. And so the structure you can consider like this. So A group is occupying the corner of the cube. The B is basically at the center of the cube, and you have these oxygen which are bonded to this B group. This is the structure of a perovskite or a calcium titanate. Now, below the Curie temperature, these particular perovskite materials, crystals, they undergo symmetry lowering distortion. So, different symmetry lowering distortions you will see below the Curie temperature. So, there are 3 phase transitions in barium titanate in order of decreasing temperature. That's at 120 degrees centigrade, you will see a transition. At 5 degrees centigrade, you will see another phase transition. And at minus 90, you will see the other transition. Finally, at the lowest temperature, they will yield a rhombohedral distortion along the body diagonal, as you can see over here. So along the body diagonal, this is the last phase transition which you see in case of a perovskite material. So the solid exists in one of four polymorphs depending on temperature. So from high to low temperature, these crystal symmetry are cubic, tetragonal, orthorhombic, and rhombohedral. So why tetragonal, orthorhombic, and rhombohedral are highlighted in blue? It is because all these phases exhibit a ferroelectric effect. Apart from the cubic, all the other three, which is tetragonal, orthorhombic, and rhombohedral crystal structure, they all exhibit a ferroelectric effect. And a cubic doesn't, because obviously it has a center of symmetry. So now, what are the application of these different, ferroelectric materials? So before we go into that, let's understand a little bit about what are the different kinds of semiconductor memory technologies which are available. So RAMs, these are random access memories, they have a symmetric read and write access time. Now, but these are all volatile memories. The RAMs, whatever we have, are all volatile memories. Now, non-volatile memories, they have traditionally been ROM or read-only memory until the advent of the floating gate technology. So, floating gate technology, this is produced electrically erasable memory such as by the flash or the EEPROM. Now, these products allow for in-system programming, but the read and the access times in this case are dissimilar. So the write access times in this case is several order of magnitudes greater than in case of the read access times. Now coming to ferroelectric random access memory, these are known as FRAMs. Now this is a non-volatile RAM. So the normal RAMs which we had volatile in nature, but in this case what you have is a non-volatile RAM because it is combining the advantages of both the random access memory and a non-volatile memory. So the write, it advantages over the flash and the EEPROM, and the non-volatility, it makes it suitable for storing data even in the absence of power. So if the power is switched off, even then it will remember where you had exactly switched off and it will get you back exactly the same sheet on which you were working on. So now what are the floating gates? I talked about a little bit of the floating gate. So a typical flash memory cell, it uses a floating gate to store a bit by the presence or absence of a charge. So this is the diagram over here, or the circuit diagram, as you can see. So if the floating gate is not charged, that is neutral, then the device operates almost like a normal MOSFET. So a positive charge in the control gate creates a channel in the P substrate that carries a current from the source to the drain. So you have the current moving in from the source to the drain. If the floating gate is negatively charged, then what is happened? Then this charge sheaves the channel region from the control gate and prevents the formation of a channel between the source and the drain. So the threshold voltage is the voltage applied to the control gate at which the transistor it becomes conductive. So the presence or absence of a charge results in a more positive or more negative threshold voltage. So in a flash memory language, what happens is the programming that is putting electrons into the floating gate means you are writing a 0. Erasing or removing the charge from the floating gate, it means you are resetting the flash memory contents to 1. So if you are just, altering the jargon of words which are using, a programmed cell, it stores a logic 0, and an erased or a flash cell, it stores a logic of 1. So you have to remember that the floating gate is completely surrounded by an isolation layer. So this enables the floating gate transistor to be used as a non-volatile memory, but it also imposes the need to find ways so that you can charge or you can discharge it. So this is the floating gate basic and the flash cells which we were talking about. So what exactly are these ferroelectric RAMs? Now, FRAM memories, these are built on the ferroelectric technology. So FRAM chip, what it contains a very thin ferroelectric film of lead zirconate titanate, commonly which is known as PZT. So the atoms in the PZT, they change polarity in an electric field. So they produce a power efficient binary switch. So when you are applying an electric field, these kind of materials, these PZT kind of crystals, they are changing their polarity. So the most important aspect of PZT is that it is not affected by power disruption, and hence it makes the FRAMs a very reliable non-volatile memory device. So if you can see over here what is happening, the cation over here is in the center. It has two equal and stable low energy states, and these states will determine the position of the cation. So applying an electric field across the crystal causes the low energy state or position to be aligned in the direction of the field, whereas on the opposite side, what is going to happen? The high energy state is going to be in the opposite position. So the applied field technically will cause the cation to move from a high energy state to a low energy state. And this transition, it produces energy in the form of a charge, which is generally referred to as something which is known as the switch charge. So therefore, when you apply an alternating electric field across the crystal, it will cause the cation to move from the top of the crystal, as you can see over here, to the bottom of the crystal, as you can see over here. So this is how it is going to shift it's continuously change the polarity. So the basic storage element, how the FRAM operates, the basic storage element is this ferroelectric capacitor. The capacitor, it can be polarized up and down by applying an electric field. So if a ferroelectric capacitor is not switched when an electric field is applied, so there's no change in polarization state. So it is going to behave like a completely linear capacitor. But the moment you are switching it, what is going to happen? There is an additional charge which is induced, so the capacitance will increase. So the ferroelectric capacitor is combined with an access transistor, as you can see over here. You also have a bit line, then you have a plate line, and then you also have a word line. And all this together, it forms the memory cell. So the write operation is again very similar to the read operation. The circuit applies an electric field in the desired direction across the ferroelectric capacitor, and the entire process goes on in the reverse manner. Now coming to so what we studied is we looked into the giant magnetoresistance effect, then we talked about the ferroelectric effect. In the last lecture, we had talked about the different ferromagnetic effect. So now we are combining all these different effects what we have studied, and now we will talk something which is known as the magnetoelectric effect. So the magnetoelectric effect is characterized by a variation of the electrical polarization P in response to an external magnetic field or an induced magnetization by an external electric field. So what exactly do we mean by this? Forget about all this mathematically. What we mean? So it means that you are varying an electric polarization. So you are applying an external magnetic field, and with that magnetic field, what is happening is your electric polarization is changing. The other way around, what happens that when you are putting in an external electric field, there is an induced magnetization in your material. So it is a combination. So by applying an electric field, you are seeing a change in the magnetization, or by applying a magnetic field, you are seeing a change in the electric polarization. So when this kind of effect you see, this is known as a magnetoelectric effect. So now let's put it into mathematical terms. This particular slide is going to give you the mathematical expressions. So this particular polarizability, electric polarizability, it is given as a function of the electric susceptibility tensor and the electric field. And on top of it, what you have is the mixed magnetoelectric susceptibility tensor, and this is multiplied with your with your magnetic field, whatever you have applied. Whereas when you're having the magnetization part, in this case, it is basically your magnetic susceptibility tensor with the magnetic field product of that. And on top of it, you're adding it along with the mixed magnetoelectric susceptibility tensor and the electric field. So these are the two different equations which gives you the magnetoelectric effect. So now what is this particular chi EM and ME? In case of EM, it is the change in your electric polarization with the applied change in your magnetic field. Whereas when you're talking about chi ME, in that case, it is the change in your magnetization with the change in the electric field which you are applying. Phi in this case is nothing but the thermodynamic potential, and this phi is basically nothing but your mixed magnetoelectric susceptibility tensor. As you see, it is delta square phi by this particular form. So the following equation in the vicinity of the phase transition point occurs. So this is when basically your chi EM is equal to your chi ME. So this is what happens in the vicinity of the phase transition point. So what is actually this magnetoelectric? That was a mathematical expression. So now let's try and understand what exactly it is. It is the phenomena of inducing a magnetic or an electric polarization by applying an external either electric field, then it will cause that magnetic polarization, or a magnetic field which will give you an electric polarization. So these effects, it can be either linear or it can be non-linear with respect to the external field. So in general, this effect, it depends on temperature, and you can represent this effect by this following equation, as you can see over here. So you have these three different kinds of phenomena taking place over here. One, you can have this electric field, you can have the magnetic field, or you can have a strain getting applied. So you have magnetization, you have electric polarization, and you have this strain factor coming in, and the mixing and matching of all these three gives you the magnetoelectric effect. So as you can see over here, these are the difference. So this is the magnetoelectric effect. When you have E and the M, they are interacting with each other, you are having a magnetoelectric effect. So these are two different types. One is the direct magnetoelectric effect and the other is the converse magnetoelectric effect. So what are multiferroics? Multiferroics are defined as materials that exhibit more than one of the primary ferroic order parameters in the same phase, and this leads to formation of switchable domains. So in case of ferromagnetism, what you have spontaneous magnetization. In case of ferroelectricity, what you have spontaneous electric polarization. In case of ferroelasticity, what do? You have a spontaneous strain. Okay. So if I am applying an electric field in case of ferroelectric material, you will see this kind of an hysteresis loop happening. When you are, and this is particularly dependent on the charge, when you are having a magnetic field getting applied, so you will find this kind of the ferromagnetic material is going to show you this kind of a hysteresis loop, M versus H, as you can see over here. Whereas in case of multiferroics, what happens is you see that when an E is applied, M changes, or when H is applied, P changes, electrical polarization changes. So ferroelectric and ferroelastic together, it gives you piezoelectric and electrostrictive coupling. If you have ferromagnetic and ferroelastic clubbed in together, what you have is a piezomagnetic or a magnetomechanical coupling. And if you have a ferromagnetic and a ferroelectric which are coupled together, in that case, what you have mixed together, what you have is a magnetostrictive or a piezoelectric coupling. So these are the different kinds of coupling effects which you can see. So in this particular case, you see you have this diagram. If you see the Venn diagram kind of thing which is shown over here, you have a magnetically polarizable materials, you have electrically polarizable materials. So many of them are completely, set apart of each other. But then in this magnetically polarizable and electrically polarizable material, you have certain subsets over here coming in. So one of them is basically, these are ferromagnetic. In the electrically polarizable materials, you have something which is also ferroelectric. Whereas when you are having an overlap of the ferromagnetic and the ferroelectric, what you have is this particular region, which is the multiferroic. And in some cases, what you have electrically polarizable material and magnetically polarizable material, these are nothing but magnetoelectric. So multiferroic is a very distinct type of material which is having both ferromagnetism. Technically speaking, it should have both ferromagnetism and it should have both ferroelectricity. So ferromagnetic and ferroelectricity should coexist in that particular material. So then it is known as a multiferroic material. So as I said, so ferroic material is basically a material which exhibits either ferroelectric or ferromagnetic or ferroelastic ordering. So a feature typically demonstrated by the presence of a well-defined hysteresis loop when the material is switched electrically, magnetically, or mechanically, as is shown in this particular plot over here. So now what are multiferroics? These are materials which possess more than one type of primary ferroic ordering in a single phase. So as I had explained in this previous slide over here, this is shown, in a better way in this particular thing. So you the same Venn diagram shown in a different way. So the multiferroic materials are either rare earth manganites. What are the example of multiferroic materials? You have rare earth manganites or ferrites or transition metal perovskite oxides. So the examples are, you can have TBMnO3, TBMn2O5, you can have holmium manganate, you can have lutetium with Fe2O4, you can have bismuth ferrites, or that is BiFeO3, bismuth manganites, BiMnO3, or you can have yttrium manganites, YMnO3. So some non-oxides are also multiferroic, such as BaNiF4 and spinel chalcogenides like ZnCr2Se4. So these are the different examples of multiferroic materials which are which has been studied in quite some extent. So materials which have the we are talking about multiferroic magnetoelectric materials now. So materials which have the coexistence of long-range ferroic order and strong coupling between pertinent order parameters such as composites based on magnetic materials as well as piezoelectric materials. So in ferrites, you have you can have composites of ferrites with barium titanate. You can have manganites with lead zirconate titanate. So on this side, you are having magnetic materials. On this side, you are having piezoelectric materials. You can have ferromagnetic materials on one side, and you can have lead, zinc niobate or lead niobate. You can have different magnetic alloys, and on the other side, you can have lead magnesium niobate or lead titanate. So you can make a composite of them, and you can have some additional control to input and store data. So different kinds of applications are there for these multiferroic magnetoelectric materials. You can use them in sensors, in multi-state memories, actuators, device applications in various biomedical fields. So all these applications are possible. Vast amount of applications are possible in case of multiferroic materials. Now, bismuth ferrite is a very important multiferroic material because it is in single phase. It exhibits magnetoelectric coupling at room temperature. So this is one of the materials which is in single phase. It shows magnetoelectric coupling, and that too at room temperature. Most of the other materials doesn't show magnetoelectric coupling at room temperature. So now in this multiferroics, let's discuss there are different types of multiferroics. One is the type 1 and the other is the type 2. What happens in case of type 1? Type 1 is shown over here, as you can see in this particular on the left side of this diagram. So in this case, what happens is the magnetic and the electric phase, they coexist within the same compound, but they have different microscopic origins, and they are mostly independent of each other. So these are the type 1 type of multiferroics. Whereas in type 2, what happens? These are single phase multiferroics in which ferroelectric order is induced by magnetism. And so it has a very strong magnetoelectric coupling. So in this particular case, you have ferroelectricity and you have ferromagnetism in the materials in case of type 1, but they have different microscopic origin and they are independent of each other. Whereas in case of type 2, you have a very strong magnetoelectric coupling because you get a ferroelectric order which is induced by magnetism and vice versa. So in this case, as you can see, if you have basically a polarization of, the polarity, the electrical polarity is shifting negative and positive. And in this case, you have a magnetic material. So you can have a spin orbit coupling, you can have a spin lattice coupling, you can have a spin charge kind of coupling. And these are these three different effects which plays around and give you a multiferroic material. So what are the different mechanisms supporting multiferroics? So ferroelectricity, it may be driven by electronic lone pairs, geometric effects, and charge order. So here the magnetic and the ferroelectric order occurs independently, and the multiferroic material is denoted as type 1, as I said. So in this particular case, there are three different mechanisms. One is the electron lone pair effect. As you can see over here in this slide, it is shown the lone pair mechanism. You can have geometric effect and you can have charge order effect. Now this so-called lone pair mechanism is based on the violation of inversion symmetry by valence electrons. So the mechanism is responsible for the room temperature ferroelectricity. So how it is dependent? It is dependent on the room temperature ferroelectricity. In case of BiFeO3, as you can see over here, the BiFeO3 material is shown over here. It has a Curie temperature of 1103 Kelvin. So here two of the Bi3 plus valence electrons, they do not participate in chemical sp hybridized states, and they create a local dipole leading to a macroscopic spontaneous electric polarization of the order of 100 microcoulombs per centimeter square. So the polarization is the primary symmetry breaking order parameter, classifying BiFeO3 as a proper ferroelectric. Antiferromagnetic G-type order with an additional long-range modulation and a small canted moment, it arises below the Néel temperature, that is around 643 Kelvin in BiFeO3. So with this BiFeO3, it has been holding the record for single-phase materials for more than half a century, exhibiting a very large electric polarization and robust magnetoelectric coupling at room temperature. But interestingly, BiFeO3 is still the only established system of its kind, and all attempts to achieve further multiferroics of lone pair type, it has failed, and including the most prominent candidates like BiMnO3. So at room temperature, it's only BiFeO3 which is going to give you this kind of type 1 kind of multiferroics. Coming to the second category, which is the geometric ferroelectricity. So these are space filling effects and geometric constraints which can cause structural instabilities in materials. If such steric effects rather than the bond chemistry leads to ionic shifts, that results in the formation of a polar state, and the term geometric ferroelectricity can be used. So the size effects and the geometrical constraints, it can cause structural instabilities that lead to polar distortions and geometric ferroelectricity. So one of the prime examples is in hexagonal RMnO3. In this case, the R can be scandium, or it can be yttrium, indium, or dysprosium as well as lutetium. So in this case, a unit cell trimerizing lattice distortion is the driving force of the ferroelectric phase transition. So as the primary order parameter is not the electric polarization, RMnO3 are referred to as improper ferroelectrics. So magnetic ordering, it emerges independently and only at a much lower temperature, at around, the Néel temperature is around 100 to 120 K. So very similar behavior is observed in case of hexagonal ferrites also. So in this case, I have given example of RMnO3, but you see these kind of things even in the RFeO3 kind of material, which has the additional advantage of a larger spin moment and room temperature magnetism. The emerging room temperature multiferrocity in this hexagonal RMnO3 or RFeO3 is appealing, but strong magnetoelectric couplings at technologically relevant length scales, that is at the level of domains, are yet to be demonstrated. Another very interesting material with geometric ferroelectricity is BaNiF4, which I discussed in the previous slide. So there is an asymmetry of the Ba2 plus and the F minus site. It induces ferroelectricity. So although the geometric ferroelectricity in case of BaNiF4 is too small to be of use in case of device applications, because the order is around only 0.01 micro coulombs per centimeter square. So it is still of profound interest as it involves a very weak magnetic order that can be reversed by switching the electric polarization. Now there is another kind which comes in, and this is basically the charge ordering. So charge carriers, they can localize and form a non-centrosymmetric superlattice leading to ferroelectricity due to the charge ordering. So long-range magnetic order and hence multiferrocity may arise at a separate phase transition. So valence electrons, as you can see, it can be distributed non-uniformly around their host ions in the crystal lattice, and they form a periodic superstructure. So a prime example in this is this lutetium ferrite, and this is considered a role model for charge order driven multiferrocity. But even after 1 decade of research, and emergence of ferroelectricity is called into question, and this continues to stimulate controversial debates. It is said that it happens because charge ordering occurs over here. It creates alternating layer of Fe2 plus, Fe3 plus ratios of 2:1 or 1:2. And there's a lot of debate going on in this particular material that whether you should call that it as a multiferric or not. Mixed mancanites also are discussed, but this does not attract very broad attention. By all indications of the literature, whatever we have right now, a charge order driven multiferrocity is an elegant concept of very strong academic interest, but whether it is going to develop into practically applicable functional materials still is, it looks a little bit far-fetched. So these are mostly, research-based work. Now, apart from this, another way to induce eccentricity in otherwise centrosymmetric structure is via magnetism, and this is where your type 2 comes into the picture. So you have this spin-driven mechanisms. So magnetic order, in this case, it can break the inversion symmetry. The interaction of spins and charges may transfer the non-centrosymmetry from the magnetic to the electric lattice, and it is going to drive the formation of a polar state. And these magnetically induced so-called improper ferroelectric materials represent the ultimate shift away from displacive ferroelectrics, in which the magnetic ordering is inhibited, towards material in which the electric polarization is induced by the magnetic ordering. So what does essentially this mean? So by definition, magnetically induced ferroelectricity is improper, and in many materials it originates from magnetic frustration. So non-centrosymmetric spin structures, due to competing magnetic interactions, they gradually evolve, and the non-centrosymmetric magnetic order gives rise to the so-called inverse Zielinski-Moriya interaction. So this is known as the inverse DM interaction. This is enabled by relativistic spin-orbit coupling, and the low magnetic symmetry is projected onto the crystal lattice and induces a very small, you can see as over here, a very small polar displacement. The polar displacement, as you can see in this particular case. The orientation of the displacement is determined by the chirality of this spin system, that is SI cross SJ. This this vector product is not equal to 0, and this yields a unique 1:1 correlation between the antiferromagnetic order and the electric polarization. So successful ongoing attempts to achieve larger polarization, which is greater than the order of 0.1 microcoulomb per centimeter square, higher ordering temperature, and viable thin film architectures reflect a substantial potential for further development and correlation phenomena that are yet to be harnessed. So the inverse DM interaction is the most intensively studied microscopic mechanism that leads to magnetically driven ferroelectricity. But obviously, this is not the only one of the interaction. There are other spin-driven mechanisms also. So one is this Heisenberg-like exchange striction. Inherently larger polarization values arise in collinear magnets with non-relativistic Heisenberg-like exchange striction. So which is proportional to this spin I into spin I dot spin J, such as in case of you have YMnO25, orthorhombic HOMnO3, or the spinel like CdV2O4. So up to now, however, ferroelectricity due to this collinear magnetism has only been observed at low temperatures. So technological applications of this particular thing, it still remains elusive. And coming to the other mechanism, spin-driven mechanism, this is the spin-dependent PD hybridization. So spin-driven modulations of the chemical bond between magnetic 3D orbitals and ligand 2p orbitals, as you can see over here, these are the 3D orbitals and these are the ligand 2p orbitals. So they yield a spontaneous polarization along the bond direction in Delafoe sites such as copper ferrites, and this is expressed by this particular relation where polarization is a factor of this SI into EJ to EIJ. So what you can say over here is that in the Delafoe sites, a spontaneous polarization occurs of around 0.2 microcoulombs per centimeter square, and this is induced by a screwed-like spin structure. This is being driven by a complex combination of spin-orbit interaction as well as spin helicity. So these are the different mechanisms which support the multiferroism. So in case of type 1, you saw 3 different kinds of mechanism. In case of spin-driven mechanism or the type 2 also, there are 3 different mechanisms. But obviously, all of them don't look promising enough for practical applications. So if you look into the comparison between these different mechanisms, ferroelectricity may be driven by electronic lone pairs, charge ordering, geometry, and magnetism. So BiFeA3 displays the largest spontaneous polarization, as you can see over here. In the relaxed state, it gives you electric polarization of 100 microcoulombs per centimeter square. And in case of, if it is strained, if the BiFeA3 is strained, in that case, the electric polarization value is almost higher than that of 150 microcoulombs per centimeter square. Among the spin-driven ferroelectrics, that is, in case of the type 2, symmetric Heisenberg-like exchange striction leads to a larger polarization than the anti-symmetric DM exchange. So this is reflected by orthorhombic TDMnO3, which experiences a transition from the spiral order to a collinear antiferromagnetic order. So the electric polarization, it moves from 0.1 to 1 microcoulomb per centimeter square under pressure. So as of now, the lone pair mechanism has been the most successful in yielding multiferrosity, that is in case of BiFeO3, with the right characteristics for device application. But frankly speaking, BiFeO3 is the only known material which is driven by this lone pair mechanism. So, but in contrast, many spin-driven multiferroic materials are being discovered, and robust room temperature systems appear to be within reach. So this is fueled by general nature of the driving mechanism itself, which leaves ample room. So here you can, play around. You can play around with the chemical doping, with pressure effects, with strain. So lot of, the materials can be actually made to be multiferroic via this spin-driven mechanism. But if you look into the lone pair mechanism, only one material is there as of now, which is BiFeO3. So now what are the type of domains and domain walls which you see in type 1 and type 2 multiferroics? This is it's a little bit important to know. So in type 1 multiferroic materials, magnetic and the electric order, they emerge independently, as we have discussed amply now in the last few slides. So the respective domain patterns do not have to coincide, and domain walls are either magnetic. In this case, as you can see, it's given as blue, or it can be electric, which is given in this form, which is basically red. If the domain patterns they coincide, then a multiferroic domain wall will form. So domain patterns coinciding, and here you will find these orange walls, which are nothing but this multiferroic domain walls, as you can see. The formation of multiferroic domain wall, they point to a coupling between the magnetic and electric order. This, however, is not required by symmetry, but in this case, you can see how thin these particular walls are. But what happens when you look into the type 2 multiferroics? Here, the magnetic order, it induces the electric order. Thus, ferroelectricity emerges jointly with a magnetic phase transition. So because of the interdependence of the electric and the magnetic order parameter, so all ferroelectric domain walls are also magnetic domain walls, and therefore multiferroic. So ferroelectric, ferromagnetic, magnetic order, multiferroic, and the ferroelectric order, as you can see, is marked over here. So you can see over here, this entire wall structure over here has lot of multiferroic domain walls. So compared to a type 1 to type 2, what you see in type 1, this presence of multiferroic domain wall is very, very less and thin, whereas in case of type 2 multiferroics, the multiferroic domain wall is clearly visible. All over what you see is basically a multiferroic domain wall. And then, of course, you have something, an important class of materials which are getting researched, and you find a lot of papers coming in the last 20 years or so. It's known as composite multiferroics. So because you lack single phase multiferroics operating at room temperature, and then they also have very weak magnetoelectric coupling. So single phase multiferroics, they are not really considered very good and attractive for applications. So you look into composite multiferroics. In case what you are having is compounds in which electric, magnetic, and piezo order states coexist within the material. But unlike single phase, which are homogeneous compounds and chemically isotropic, composite multiferroics are characterized by the fact that these order phases, they are physically separated from each other within the multiferroic composite material. So, but in this case, what is going to happen? The resulting magnetoelectric coupling, it can be 108 times larger than case of single phase multiferroics. But the only problem is that it is observed only at microwave frequency and in a very limited range of operation conditions. So a lot of research still needs to be done to get this, the ideal kind of material which can be practically have a lot of applications. So conditions for a strong magnetoelectric effect in composite. So both the individual phases should be in equilibrium. Mismatching of the grains should not be there. The magnitude of your magnetostriction coefficient of the piezomagnetic or magnetostrictive phase and the magnitude of the piezoelectric coefficient of the piezoelectric phase, they must be very high. Accumulated charge, it must not leak through the piezomagnetic or the magnetostrictive phases. And the strategy for poling of the composites, it must be determined. So there are a lot of application of these ferroic materials. You can have them in memory devices, sensors, transceivers, amplifiers, transformers, phase shifters, displays, wave filters, generators. So there are a lot of application in case of these different kinds of ferroic materials. So here one particular example what we'll see is the AC and DC magnetic field sensors, how it works. What are magnetic sensors? These are devices that can detect without physical contact the creation or variation in magnetic fields of the surrounding environment. And from these changes, they will derive information on the properties of the magnetic field itself, as well as indirect properties of other entities such as direction, presence, rotation, angle, speed, electric current, temperature, and so on and so forth. So what is the magnetoelectric voltage coupling coefficient? This is alpha V H, and your V, this particular voltage, is a function of this external electric field, whatever you are applying. So T is the thickness of this ferroelectric layer in case of laminates, or the thickness of the sample in case of a single phase composite. Whereas H is the amplitude of the magnetic field under measurement, and V is the voltage response of the multiferroic sensor. So this voltage response is dependent on all these different factors. So a linear response is a critical requirement in order to operate as a sensor. So coupling measured at intermediate angles between 0 and 80 degrees, it shows almost a linear variation. As you can see from 0, you can almost see a very linear variation of the sensor's response. This indicates the possibility of utilizing these multiferroic sensors for direction detection as well as for compass applications. So you can have these AC-DC based magnetic field sensors made out of multiferroic materials. Then you can have multiferroic microwave resonators which are tuned electrically. So ferromagnetic materials subjected to high frequency excitations display ferromagnetic resonance. So this is basically the idea. So if you have ferromagnetic material, you are subjecting them to high frequency excitation, what you will see is a ferromagnetic resonance. Ferromagnetic resonance will occur when the frequency of the precision matches the frequency of the excitation field, and this typically occurs at microwave frequency in ferrite materials. So radar and communication technologies require rapid switching from one operating frequency to another with minimal power. So by replacing the ferrite materials with a multiferroic bilayer composite, electric field tuning of this ferromagnetic resonance will be possible. So as you can see, the effect of the applied electric field can be viewed as the creation of an internal magnetic field, which is responsible for the shift in this FMR curves. So this is how this is going to look like, and this is how it is going to work. Now, other very important application for which multiferroics are getting developed is multiferroic magnetic recording reed heads. We already saw the reed heads which are made of GMR kind of materials. So now let's see what is the application of multiferroic magnetic recording reed heads. So new reader technology, this is based on magnetoelectric effect in multiferroic materials rather than the traditional magnet resistance effects. So the sensor stack is what? It is a planar structure that incorporates a trilayer, which is a ferromagnet, a ferroelectric, and a ferromagnet multiferroic composite structure. So this operates as an AC magnetic field detector via the magnetically induced magnetoelectric effect. So essentially what happens? As the head is moving along the magnetic recording track, the field from the recorded beat provides an AC excitation field to the multiferroic reed head sensor. Now in order to induce a strain-mediated magnetoelectric effect, a DC magnetic bias field is also required. So the best way to bias this multiferroic composite sensor is via a self-biasing mechanism using an exchange bias effect between a ferromagnetic layer and the antiferromagnetic layers, as is shown over here. So now what is the advantage? So you will have very reduced power consumption, then you will have improved thermal performance as the multiferroic reader is capacitive rather than being resistive, and you have a very higher operation frequency and thinner reader containing maximum 7 layers, which allows magnetic recording densities of 1 terabyte per inch square and beyond. So you can imagine the amount of data which can be actually recorded on these particular read heads. And then you also have multiferroic random access memories and multi-state memories. So when magnetic order and electric polarization, these are simultaneously displayed, a multiferroic element could essentially combine the advantages of a FRAM and MRAM, and it can form a non-volatile random access memory with multiple memory states. So two binary states could be encoded by a ferroelectric polarization state and by integrating the multiferroic within a magnetoresistive multilayer. So two additional binary states could be encoded in the resistance state of the multilayer stack. So what is happening in a nutshell? It is shown in this particular plot. So all whatever I am discussing right now, this is very nice pictorially represented in this particular plot over here, this particular diagram over here. So you have one type of resistance, you have another type of polarization, you have another type of resistation, another type of polarization, and if the R varies, the polarization varies. So four different states are possible. So strain-mediated magnetoelectric coupling in multiferroics. This is utilized to achieve the magnetization rotation of the free layer. So what you have in this case, MF RAM could operate as an all-electric read-write four-state memory RAM, offering therefore less power consumption, more memory density, and non-volatility simultaneously. So this is what is, in a nutshell, how your multiferroic random access memory and multi-state memory is going to work. So today's class we will end over here. If you have any questions, I am ready to take it right now. So this particular lecture, please remember, it is having a lot of devices, lot of the different kinds of terminologies over here, biasing, reverse biasing, coupling. So all these different effects are there. So in case you have any doubts, I am right now over here. You can clarify it from me. Go through the lectures once again because I know it's a lot of material to get assimilated in such a short time. But just listen to the lecture again and again. And I have most of the time in the slides, I have given all the different points which are covered. So it is easier for you when you look into the slides and listen to the lecture once again. In case you have any doubts, please clarify it now. Or else my email address is there. You can always email me for any particular doubts. So in case there is no doubt, I'm sure there will be many doubts when you actually you will be actually looking will be listening to the lecture properly maybe once again or looking into the slides. So as and when you have them, kindly get it clarified, because this is definitely a little bit complicated, this particular entire series. So I've tried to make it as simple as possible, but still I'm not able to simplify it further than this. So in case you have any doubts, please write an email. Since I don't see any doubts in the chat section, so I'll call it a day. Have a great evening and enjoy the rest of your day. Thank you.